Start with the lab. So make sure on questions 4, 8, and 12 that you have mentioned all 4 variables in this equation. Centripetal force equals mv squared over r. Okay? Make sure that you have, in 4, 8, and 12, make sure you have mentioned all 4 variables. Okay? I say again, all 4. All right. And when you do those calculations on number 13, so you're going to use centripetal force equals mv squared over r. You're going to go to your data table. You're going to find whatever your velocity is for number 4. Make sure that you're using the mass of the stopper, that radius. You're going to calculate the centripetal force, and then you're going to compare that to the weight that's hanging down, because that's what's creating that centripetal force. And so like on this one, you're going to have a theoretical value of 3.92 because you had a 0.4 kilogram mass. So you're basically going to take whatever you get out of that minus 3.92 divided by 3.92 times 100. Okay? And this is like an absolute value. So you take the mass of the stopper minus velocity squared divided by the radius. You're going to get a number. Subtract that from 3.92, divide by 3.92, multiply it by 100, and absolute value kind of thing. Send on, you're going to do the same thing on 8 and 12. So then on number 14, you're going to calculate your centripetal acceleration using v squared over r. Calculate that. Then when you get that answer, divide that by 9.8 meters per second squared to get your g's. Okay? Now, on number 15, you should get a really big number on number 15. Okay? You should end up with like something times 10 to the 22nd newtons. So you're just going to use, on this one, just use mass 4 pi squared r over t squared. But again, pay attention to the fact that that radius is in kilometers and that period is in years. Okay, so you got to convert the kilometers into meters and the years into seconds. Now, on number 16, so you have a 70 kilogram person standing on this earth, this rock that we're on, and the rock is spinning. Now the earth is actually slowing down a little bit as it spins, so not enough to really make any difference, but they figure it used to be, they think when the earth was kind of first formed, a day was actually like 12 hours, but we slowed down because it's just like a spinning top. Okay, you're going to slow down over a period of time. So every once in a while we actually have to adjust the world's clocks because the earth is slowing down a little bit, so we have to make adjustments in the earth's clocks. Not enough to really make any difference, but yeah, eventually the earth is just going to slow down as it spins. Part of that is because there's a tidal pole on the moon, and because we have tides, that's actually kind of impeding the motion of the earth, and that's kind of what's making it slow down. Don't worry about it, it's not going to impact your day, you know, it's okay.
We should get out of school early.
Okay, again, not enough to make any difference. All right, so here's one of the things that you look at. So here's this person standing here on the earth, and you can calculate the gravitational attraction between this person and this strange rock that we're on using mg. Okay, so if I said, hey, what does a 70 kilogram person weigh? Oh, you can take 70 kilograms times 9.8 meters per second squared. Okay? And you're going to get about 700 newtons, okay, roughly. So there's about a 700 Newton force of attraction between this person and the earth. So what you're going to calculate on number 16 is how much centripetal force is needed to keep that person on the earth as the earth spins, okay? And what you should see is that your answer to number 16 is much less than 700, okay, like a lot less. So, and that's a good thing. Because if the centripetal force needed to keep this person on the earth was bigger than 700 newtons, guess what? We wouldn't be here on the earth. It would be like the little, the green spinning thing where he put the quarters on there, okay? And it began to speed up. Well, it just wouldn't work, right? So you have to have more centripetal, your gravitational force has to be bigger than that centripetal force needed to keep you on the earth. So anyway, so your answer to number 16 would make a not so good GPA. Okay? A not so good GPA. All right. Any questions on the lab? Make sure that you've got, yes, Matt?
So for number 17,
Yeah.
free body diagram, did you want us to draw the force gravity vector acting on the stopper, or is that good?
Hold on. Okay, here's the deal. As this thing is going around, right?
Right.
Is gravity pulling down on it?
Yes.
Yes. So that's one of the forces that you have to have.
Okay.
So look, you know the mass of the stopper, right? Multiply that by G, there's the downward force acting on the stopper.
Okay.
Yeah, you have to have that. That's one of them that you have to have. And make sure that you draw that to scale. Okay? All right. Anything else? Once, twice, sold? Okay, that's done. All right, any questions on the, Gara, is that a question or
Purple?
just a stretch?
No, purple?
Yeah?
Yes.
Which one?
So 8, 9, 10. I did them, but I don't think they're right.
8, 9, 10?
Yes. So 8
Okay,
is it around 11, 12?
no.
No, lovely. Okay.
Okay, so on 8, that's the guy throwing the hammer, right?
Yeah.
Okay. So here's this hammer throw, right? Which is basically a big steel ball on the end of a cable and swinging it around. So you're just going to go, oh, centripetal force equals mass 4 pi squared r over t squared. So you got the mass, the 5.27 kilograms, right?
Mm-hmm.
Got that number. You know 4 pi squared. You've got the radius of 1.83 meters. Okay? Now the tricky part comes with the period. So on that one, you're told that you're making 2 revolutions per second. Now, is that frequency or is that period?
Frequency. Period.
No, that's frequency. You're fine. Okay? Because it's revolutions per second.
Mm-hmm.
Okay? So that's frequency. You need period. So what are you going to do with revolutions per second?
Do the inverse.
Yeah, so that just becomes
0.5.
0.5 seconds squared.
I did the mv squared over r. And I put the v, the velocity, as 2 meters per second. I didn't convert it.
Oh, no, that's not even meters per second. That's,
I know. I don't know what I'm doing.
yeah. Yeah, you've got to use 4 pi squared r over t squared and set that period as a half a second. Okay?
Mm-hmm.
All right. So on number 9, number 9 is a similar type thing. Okay? So on number 9, here's your centrifuge, right? And that's what I showed you yesterday. So this thing spins really fast. That's how it works. Okay? So you're spinning at 5,000 revolutions per minute, which is per 60 seconds. So you need to take 5,000 and divide that by 60, and that gets you revolutions per second.
Mm-hmm.
Then you need to take the inverse of that, and that gives you seconds per revolution, which should be a really small number, okay? Because this thing is spinning really fast, right? So it doesn't take much time for each revolution to take place, okay? Then, once you get that number, and you're just asked to find the centripetal acceleration, just go 4 pi squared r over t squared.
Is it something times 10 to the 4th?
It is.
Okay.
So all of your answers on number 9 should start with a 4. Okay? All of your answers should start with a 4. And your answer to 9A should be something times 10 to the 4th. So your answer to 9A is 4 times something times 10 to the 4th. Okay? And then to get your G's, just take your answer, you get your answer from B, just take your answer from A and divide it by 9.8 meters per second squared. So your answer to B should be like something times 10 to the 3rd. So what that means is if someone shrinks you down, okay, have you ever seen like the Marvel movie like Ant-Man? If someone shrinks you down and wants to put you in a centrifuge and spin you around, don't do it, okay? You are going to get absolutely crushed, all right? Because, like I said yesterday, most people pass out at about 3 or 4 G's. This is going to be like, times 10 to the 3rd G's. You are not going to survive, okay? So if someone shrinks you down, don't let them put you in a centrifuge. On number 10,
There go my weekend plans.
I know, sorry Matt. So on number 10, so here's the Mini Cooper, okay? And you want to experience the same acceleration as like a Mustang taking off going really, really fast. So you just want to go, oh, I can calculate my linear acceleration. A equals V minus V naught over time. So you can calculate the linear acceleration of the Mustang and then set that equal to V squared over R. So find your linear acceleration, use that as your centripetal acceleration. You know the radius, figure out how fast you have to go. So both of your answers on number 10 should be around 5. Okay, that's an ish, but both of those answers should be around 5. Okay. Make sure on 3 and 4 on the problems basically are the same idea, where you have centripetal force equals mv squared over r, okay? And on both of those, you're solving for velocity. So it's just centripetal force times r divided by mass gets you your velocity. So your answer to number 3 should be something around your current age, and that's an ish, okay, it's an ish. And your answer to number 4 should start with a 4. Okay? And your answer to number 7 should be a pretty small number for the centripetal acceleration of the Earth as we fall around the sun. Okay, are we good? Once, twice sold? Okay. So I'm handing out these lecture notes, okay? Okay, there we go. All right, so the one thing we haven't talked about so far is how gravity plays a role in okay. All right. kind of flipped out there for a second. Okay, is how gravity plays a role. Because right now, everything that we've talked about has been motion like this, where it's been in a horizontal plane. But a lot of times, we're going to have centripetal motion in a vertical plane like this. So as I swing this thing around like this, so now I'm going to swing it around in a vertical circle, okay? So instead of going horizontal, now I'm going to be going like this, right? So here's the question. As this goes around in a circle, when is the string going to be most likely to break? Okay, so I'm going to swing this thing around in a circle like this. When is the string going to be most likely to break? When is it under its maximum load? When it's at the bottom, when it's at the top, or when it's at the side?
Bottom.
Why, Matt?
Because
Your answer is right, but why are you right?
gravity's pulling it down, so it's accelerating on the way down this way as opposed to this way. Well, this way in addition to that way. So you have to go back up. You have to counteract both the acceleration of gravity and
Killing it.
It's actually not bad, okay?
it's moving fastest at that point.
No. I'm assuming there's moving at the same speed.
Okay, well then, never mind.
No, your answer is still right, okay? So here's the deal. So let's look at what's going to happen at the top and what's going to happen at the bottom, okay? Now, let's just look at this. Leave gravity out of the mix, okay? Don't worry about gravity for now. Do not worry about gravity. If this thing is just moving in a circle, do I have to keep applying a force to it to keep it moving in a circle? Matthew?
Yes.
Yes, because what does the rubber stopper want to do? It wants to fly off in a straight line because of Newton's first law of motion. So, just to make it move in a circle, right? To make this thing move in a circle, I always have to have a certain amount of centripetal force acting which direction? And at to the
Velocity
vector. Because at any given point, this thing wants to fly off on a straight line tangent, right? So that's going to be at a right angle. So I know as this thing goes around, at a minimum, I have to have enough centripetal force to make it move in a circle. Okay? Everybody cool with that? Got to have that. Now, and that centripetal force, you could view it as being mass times your centripetal acceleration. You could write it as mv squared over r. There's any number of ways you can write this thing. Now, and that's going to be true no matter where I am in the circle. Now, don't worry about centripetal force. Okay, leave centripetal force out of this thing. Okay, I'm just going to hold this thing up. So, how much upward force does the string have to provide? Enough to balance out what, Kara?
Gravity.
Gravity. So my string has to provide the normal force. If it's sitting on the table provides the normal force. If I'm holding it up, the string has to provide the normal force. So when it's at the bottom, the upward force has to balance out gravity. So this is why it's going to feel most heavy at the bottom, because of the fact that you have to provide two things. So the total force at the bottom is going to be the centripetal force that you need to make it move in a circle, plus the force to overcome gravity. Okay? Now, when you're at the top of the loop, okay, right? Now, gravity is actually helping you out, okay? Gravity is providing some of that centripetal force because gravity is acting downward. So, when you're at the top, the total force that you feel is going to be Fc minus Fg. Now, you all intuitively understand this equation, and I'm going to show you why in just a second. So, if you look at this video, okay, And so let me show, let's see this. So this is like a computer animated version of a roller coaster, okay? What? Oh, there we go. Now, you automatically kind of feel heavy, like you can feel this in your stomach. So when you go down, whoa, you feel heavy, right? Now, notice when you come up over the top, okay? Now, at that point, when you were coming up over the top, what did your body want to do when you got to the top of that hill? What did your body want to do? Body wanted to fly off in a straight line, right? Okay? But you were still accelerating because your body was changing direction, okay? So there had to be some downward force to make your body not fly off in a straight line, okay? And gravity was providing part of that. So when you're coming up over the top of that hill, you feel lighter because your body wants to keep going straight. When you're at the bottom of the hill, right, you feel heavy because at the bottom of the track, your body has to keep you from being pulled down by gravity, and it also has to change the direction of your velocity vector, okay? So at the bottom, you feel heavy. At the top, you feel light. I'll come back here. Ooh. Feel light. Whoa, and we're back. Okay. That'll be the next one. Okay. So here's the deal. So at the top, your force total is force centripetal minus Fg. And at the bottom, okay. Now, this total force is what you feel, okay? It's what you experience. So, at the bottom, you feel heavier because not only do you feel the effects of gravity, you also feel the additional force that's making you move in a circle. At the top, you feel lighter because your centripetal force is being, that gravitational force is being subtracted from that centripetal force. Now, this is, I'll say this again and again and again. This is what you feel, okay? This is what you experience. Now, up at the top of the flight, you can experience what we call weightlessness. You can be in a state of free fall. So, up at the top, we can set that side equal to 0. Okay? Force centripetal minus Ft. You can experience weightlessness, and that's the next video that I'm going to show you. So as you come over to the top, okay, so as this rubber stopper comes around over the top, so as that thing is coming up over the top, for a brief second, that thing is in a state of weightlessness, because the centripetal force that you need is being provided by the gravitational force. Okay? So we're going to be in a state of weightlessness for just a split second. So if you set this equal to 0, and then I'm going to move that Fg over there. So I'm going to have Fg equals force centripetal, and that's going to be mg equaling mv squared over r. So right away, Shivani, what can I do with my mass? Cancel that out. Okay, so that's going to go away. So I kind of get a canine equation if I solve for v. So if I multiply by r, I get the square root of GER. So what this is telling me, this is the minimum velocity that I have to complete a loop. So if you look what happens. If I'm not going fast enough, okay, when I swing this thing around, I don't complete the loop. But if I'm going fast enough, then I will. So there's a minimum velocity that I have to complete the loop. So what's going to happen is that this is going to tell you how fast you have to be going. Now, if you want to be on the safe side, you want your centripetal force to be bigger than what gravity can provide. So let me show you how that works with the roller coaster. So let's go to the back. Okay, so the whole thrill of a roller coaster is the fact that you're changing your velocity vector. Constant velocity roller coasters are boring. So as this thing is coming in here like this, right, it's going to come down. Now, if this is just sitting right here at the bottom, if it's just sitting, not moving anything, imagine that you have like a bathroom scale. So you're at Worlds of Fun, and you're on the roller coaster, and in the name of science, you bring a bathroom scale with you, okay? And you sit down on the scale, okay, like this, and you're sitting on the scale, and you look down, and let's say it reads 80 pounds, okay? All right, 80 pounds, boom, here you go. So if you're just sitting right there, you'd be reading 80 pounds. Now, when this thing actually comes down, and you're at the very bottom of this starting to turn, if you were to look down, is that reading going to be bigger than 80 pounds or less than 80 pounds?
Bigger.
Bigger, because not only does that scale have to keep you from being pulled down to the center of the earth, it's also reading the additional force that's making you go through the circle. Now, when you get to the top, okay, so if you could look down, if you were at the top, then that reading might be less than that. It might be like 40 pounds or something like this. So if you're not going fast enough, bad things are going to happen, okay? Because you haven't met that minimum velocity. But if you are going fast enough, okay, then,
Bad things still happen.
well,
Well-
at least you made it through the loop. That was after you made it through the loop. So, in terms of making it through,
Oh, no.
that
That
was really
was,
bad. Yeah.
This is why I don't.
That was even worse. Okay, we'll try this one more time. Come on.
how many
There we go.
waivers has that car had to sign?
That one made it all the way around. Okay, that was a good one. So, this would be the ultimate roller coaster to build. You can call it the 0G roller coaster. Okay? If you knew that you were going that exact velocity just to complete the loop, you could take out the middle section up here. You call it the 0G. And if you knew you were going just at that exact speed, then when you hit the top, you wouldn't need this part of it, because gravity would be providing just the right amount of force to complete that loop. Okay? Now, the problem is if you're not going fast enough, then you're going to have some action like this. If you're going too fast, you're going to overshoot it and hit here. Now, there's not an insurance company in the world that would touch you, okay? But it would be really, really cool because people would, you pull up to the park and the top section of that loop is missing, okay? And for a very brief amount of time, you would be in a state of weightlessness. Now, realistically, you want to be going faster than that minimum velocity. So you want to feel something, okay? So, really heavy at the bottom, light at the top. Heavy, light, heavy, light. Got it? Good? Okay, back we go.
Here.
We have to have the exact same weight in order to get that same velocity.
Okay, now, what you're going to see in this next video is a company called, oddly enough, Zero G. And they take a plane and they fly you in these big arcs, okay? And what allow you to experience is different gravitational fields. Like the first one they experience is Martian gravity. Martian gravity is about 1/3 that of the Earth's gravitational field. So if you look at your force total equaling force centripetal minus Fg. So on the first one that you see, you experience Martian gravity. So you set this equal to 1/3 Fg. You want to experience 1/3 of what you weigh right now. So if you want to lift your arm would feel 1/3 of what it normally does. If you did a push-up, okay, it would feel 1/3 as much force as it does right now to do a push-up, okay? So that's going to equal force centripetal minus Fg. Now here's where the magic happens. I'm going to move this Fg over here. So when I take 1/3 and add an Fg to it, Ms. Pfeiffer, what do I get?
4/3.
Yeah, so I'm going to get 4/3 mg, which is how we're going to calculate our weight, right? Which is going to equal mv squared over r. So here's what's important. Mass cancels out, okay? Could be Matt, could be Shivani, could be me. Doesn't make any difference. So if I solve this for velocity, okay, I'm going to multiply by r, and then I'm going to take the square root of it. So I'm going to get v equals the square root of 4/3 girth. So if you're the pilot, and you know the radius of the arc, this tells you how fast you have to be moving to experience Martian gravity. Now, the next one they're going to do is lunar gravity. Lunar gravity is about 1/6, okay? So you would have 1/6 Fg equals Fc minus Fg. The only number that ever changes is this. And the last one they're going to do, they're going to be in a state of weightlessness, whereas 0 is going to equal Fc minus Fg. So this is what's going to be important. This is what you are going to feel, okay? So,
to recreate zero. In the early days of space exploration, NASA developed a technique to recreate zero gravity, the notorious vomit comet. Because the weightless effect of microgravity is nothing more than a continuous free fall, it's possible to simulate it by flying an aircraft in a huge arc or parabola, which, for short periods of time, allows
usually about 25-30 seconds.
as though it's space. But the stomach-churning ride could spell trouble for some people. All right, I know what you're thinking. I've got this Achilles heel of the motion sickness. Of course, you're all expecting me to throw up, but I'm not. So, into another flying machine, and into another stylish flight suit. I joined a group of eager participants, including entrepreneur and astronaut Richard Gary, one of a new breed of self-funded space tourists. This is one of the only privately funded training facilities, offering the public a rare opportunity to cheat gravity in this specially modified Boeing 727. Once in the air, we climb up to 7,300 meters to start the first of 12 parabolas. Here we go. This very first parabola is going to be partial gravity, so 1/3 my body weight. I can immediately feel myself detaching from the floor of the plane. What are push-ups?
I could even do that.
Okay, lunar gravity.
So now this is 1/6.
Just let your body float. Go on, enjoy what it feels like. Just feel your body completely relaxed in the air.
The parabolas are becoming increasingly severe. Basically, I'm skydiving inside the aircraft. That is so strange.
Go Team Silver!
This weightlessness thing is pretty cool. You only get short periods of time, maybe 20 seconds, 30 seconds at a time, but it's just like being in space.
We're all gonna be facing that way, right? You're gonna kneel and you're gonna try to crawl as fast as you can, okay? Okay? Alright, here we go.
Yeah, sure, okay.
Go, 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 go! Woo!
I can now better understand how difficult it must be to relearn every physical task during a prolonged space flight. But hey, that is just the most unbelievable experience. We're now completely weightless, able to fly like Superman. The constant pitching of the aircraft is pretty intense. And by parabola 10, the effects are starting to hit.
Okay.
If I were to do that, I'd be mad if there were that many people in there.
Yeah, it's like, get away from me. That's what I want.
You keep bumping into me, I'm trying to feel weightlessness.
Yeah, get away from me. Okay. So this is why it's called the vomit comet. It's because when you're at the top of the parabolas, you're feeling like weightlessness, okay? But then when you hit the bottom of the curves, then you're going to feel really, really heavy. So you're going to go from states of weightlessness, okay, to states of feeling really, really heavy. Now, you can't ever feel weightless at the bottom. You can feel weightless at the top. And the reason that you can't feel weightless at the bottom is that you have force centripetal plus Fg. So even if you're at level flight, you're going to feel like you do right now. If you add in the fact that you're traveling in a circle, that's even going to add more force to it. So your only chance of being in weightlessness or some variation on that is going to be at the top. Okay, so listen to me. What you're going to have, right, to get that is at the top, you subtract. At the bottom, you're going to add it. So here's what I'm going to do. So then we're going to turn the lights on. So I've got this cup of water, okay, legitimate cup of water. And I'm going to swing this thing around in a circle. And I want to calculate the minimum velocity that I have to complete the arc, okay, so that I don't get wet. So here's the deal. So at the top, to get my minimum velocity, I'm going to use V equals the square root of GERT. So the only thing I need is the radius. So somebody estimate the radius from my shoulder down to the cup. Kara, ballpark it in meters.
1 meter.
Okay, 1 meter. That'll make the math easy. So here's my arm, right? We got the cup. And Kara said that's about 1 meter. So, Matt, take your calculator. Take G times 1 meter and then the square root of that.
3.0.
3 point what?
1-3.
3.1 meters per second. So if I'm going to do this and stay dry, at a minimum, I have to be going 3.1 meters per second. Realistically, I want to be going faster than that. I want to be going faster than that, so up at the top, when I subtract, I want this to be a positive number. So I want to need more centripetal force than what gravity can provide. Because I want this difference to be a positive value. Okay.
Is it weird on there?
Huh?
Is it like stuck on the platform?
No,
Okay.
it's not. Okay? I'm just sitting with you. Okay? You ready? Okay? So, what this means, because it's completing the loop, that means that I'm going faster than that 3.1 meters per second. Now, I'm obviously not going to do that because I don't want to spill water, but what it would look like if I wasn't going fast enough, then it would do something like that. So, what's happening is that here's this platform, okay? And here's the cup. So, there is a certain amount of force that I have to have provided by this platform, okay? Gravity is providing some of it. The platform is making up the difference. So if I could have like a little scale between the platform and that cup, okay? That scale would tell me how much force is actually being provided by the cup. Now, here's one thing I want you to get out of your minds right now. This thing doesn't complete the loop because there's some force pushing it up. There is no force pushing it upward, okay? There's nothing there. It isn't like I swing this around and my body emanates this magic force that's pushing it against the platform, okay? It's not what's happening, okay? It's just going fast enough that that platform is providing a force that's acting inward, so it just keeps that cup from flying off, okay? So there is nothing pushing it out. There is no centrifugal force, which means outward seeking. There's just an inward force from the cup, okay? Got it? Good? Okay. All right. Now, here's the last thing. So, has anybody been to Worlds of Fun and rode the ride where you're inside the barrel and it starts spinning and they drop out the floor? Has anybody ridden that?
Not at Worlds of Fun.
Okay, but you know the concept, okay? So here's the basic idea. Is that you walk inside this big barrel and you lean up against the barrel and imagine that this room is starting to spin, okay? And the room spins faster and faster and faster. Then at some point, they actually lower the floor out from underneath you. And you're like stuck up against the wall like this. Now, this is a classic example of what you feel. You're going to feel like, oh my God, I'm being pushed. That's how I got a brother-in-law that cannot say the word push. He just pushed, okay? So, if you're inside, you're going to feel like you're being pushed up against the barrel wall, okay? But let's look at the dynamic. So I'm going to take this, I'm going to put this rubber stopper on here, okay? And now I'm going to start to spin it around in a horizontal circle, okay? So I'm going to spin this thing around in a horizontal circle, and what you'll see is that the rubber stopper stays there.
Does it?
But if I slow down, then what happens?
It does not.
It does not, it begins to fall.
It says, alright, I'm head
I
out.
thought that was the water at first, and I was like, oh.
Oh, no. Okay, so let me do that again, right? So I swing it around, I'm going fast, but then if I slow down, then it falls. So clearly, there has to be some amount of force or some minimum velocity that it takes to hold it on. So if you look at the forces that are acting on this thing, okay? So here's my platform, right? And there's the rubber stopper. So when that's sitting there, what's one force that's acting on the rubber stopper no matter what?
Gravity.
Gravity, okay? So gravity's trying to pull it down, right? Now, just by virtue of the fact that it isn't falling, what else has to be there? There has to be a centripetal force which is going to act which way? Inward. So there's going to be some centripetal force acting on it, right? Now, there has to be something to balance out gravity, right? So there's going to be some frictional force that's acting upward to balance out gravity. Now, at a minimum, what has to be the relationship between force, friction, and gravity to keep that thing from falling? What'd you say?
You have to be the same or not.
They have to be the same. At a minimum, my frictional force has to equal my gravitational force. At a minimum, okay? So, these are the three forces that are acting on this thing. And I know I'm accelerating because my forces don't add up to equal to 0. My acceleration is acting inward because that's the direction of my imbalanced force. So, we're going to go back to mu equaling forced friction over force normal. Basic definition of mu, right from the get-go, right? Now, my forced friction has to equal my gravitational force. Now, if you go back to inclined planes, right? If you're on an inclined plane, remember the normal force is acting like this. So, and I get steeper and steeper and steeper, and that normal force still acts like this. So if I go completely vertical, the normal force is my centripetal force, because that's what's acting at a right angle to the surface of the platform, okay? So I'm going to, instead of normal force, I'm going to have that being my centripetal force. So then I can go, oh, that's mg, that's mass times my centripetal acceleration. My masses cancel out. One version of this is you get g over ac. So here's how this plays out. So let's say here's this ride, okay? And let's say that the radius is, I don't know, 4 meters. And you know that the coefficient of friction between people's clothes and the surface is 0.5. Okay? So you know mu is 0.5. You know what g is. And I want to find the centripetal acceleration. So here's my question. Ms. Pfeiffer, how can I get my centripetal acceleration by itself?
Multiply it and divide mu.
Okay, beautiful. So, my centripetal acceleration is going to equal g divided by mu. So Matt, take 9.8 meters per second squared and divide that by 0.5. And you should get 19.6, I think.
Oh, never mind.
Right?
Hmm?
So here's the deal. If you're inside this ride, okay, that's going to be your, at a minimum, you're going to experience 19.6 meters per second squared of your acceleration, which is going to be like 2g. So if you're inside this ride, and you go to like, you're going to be like this, right? And you go to lift your arm is going to feel twice as heavy as it does right now. When you go to like lift your head off of it, your head's going to feel twice as heavy. This is why you get this sensation like you're being pushed. Now remember, you're not being pushed outward. Your body just wants to move in a straight line. So you're feeling the action-reaction force between the wall and you, because you want to move in a straight line, and this barrel wall is keeping you from going this way. So, now from here you can do a bunch of different things. If you know the radius, and you know, oh, centripetal acceleration equals v squared over r. So if you know the radius, which is 4 meters, you can calculate the velocity that you're moving at. So Matt, let's do this. Take 19.6 meters per second squared, multiply that by 4 meters, and then take the square root of that.
8.85.
8.85 meters per second. So that's how fast you have to be going at a minimum, so that when they lower the barrel wall, you don't slide down. If you're going faster than that, that just means that you just have you have a safety margin built into it. Okay? Got it? Good? Okay. Okay, so let me stop that. I thought I had mine, but I don't. Okay, so on this centripetal motion assignment number 3. So let me kind of paint you the picture about what's going to happen on these. So on number 1, you're moving around in a vertical circle like this. Okay? You're going to be going around like this. So I've given you the radius. You got a 2 kilogram mass. Okay? And it's hooked to a scale that's measured in newtons. Okay? Not kilograms, measured in newtons. So what value does the scale read when the mass is moving at 4 meters per second at the lowest point? So you're here. You're going to go force total equals force centripetal plus Fg. So you take your centripetal force, add that to your gravitational force, you should get a big number. Now, then I say, is the mass going fast enough to complete the loop? So up at the top, are you going fast enough? There's like 3 different ways you can answer this question. You can calculate the minimum velocity that you need using v equals the square root of GR. And if that's bigger than that minimum velocity, you'll complete the loop. You can calculate the total force at the top. If that's a positive number, you'll complete the loop. If your centripetal acceleration is bigger than 9.8 meters per second squared, you'll complete the loop. Okay? So there's like 3 different ways you can answer 1B. When you get to number 3, here's the setup. You're in a car and you're going over the top of a hill. Now, what's different about number 3 is that you still have the hill to help you out. So, because the hill is going to be there, it isn't like I'm swinging this thing around on an inside loop. You're actually going over the top of the hill. But again, you're going over the top. You're going to go force centripetal equals force total is Fc minus Fg. When you get to question number 4, you're in a roller coaster. You want to calculate a whole bunch of different things. So on number 4, what you're going to do on number 4, you're going to start with force total equals Fc minus Fg, because you're going to be at the top of the loop. So what you want to do is you want to calculate what's the speed required for half his actual weight, 3/4 his actual weight, 1/4. So what you're going to do on number 4, you're going to go over here and go, okay, like if you want to feel 1/4 your weight, you're going to go, oh, I'm going to have 1/4 Fg equals Fc minus Fg. Now, if you do a little bit of mental math, this becomes 5/4 mg equals mv squared over r. So all I did was I added an Fg over here, and that's where the 5/4 came from. Fg is just mass times my gravitational acceleration. And this is mv squared over r. And again, what you'll see is the mass cancels out. So you're going to get v equals the square root of 5/4 girth. This tells you how fast you have to be going to experience 1/4 your force weight at the top of the loop. So the only thing that's going to change is this fraction. Next thing you want to feel 1/2 your weight. Next one you want to feel 3/4 your weight. So the only thing that changes is this fraction right there. Okay. When you get to number 9, okay, I've given you 22 revolutions per minute. What do you have to change that into? Seconds per revolution. Okay, I am done. You are on your own.